ওকে, সো আমি ওইগুলো আপলোড করে দিয়েছি, দেখেছো বোধহয় আগেরগুলো, লিনিয়ার রিগ্রেশন আর লিনিয়ার অ্যালজেব্রার বেসিক, দেখেছো?
হ্যাঁ ম্যাম, দেখেছি।
Okay, so we will move on to the next topic. I mean, the reason we studied little bit of linear algebra, so we will see all its uses in today's class. So we will be talking about dimensionality reduction. So there are several ways you can do dimensional reduction. So what is the meaning of dimensionality reduction is that you have a huge data matrix, and maybe some of the attributes are somewhat correlated to other attributes, and so blindly working on that entire data matrix will make the model, whatever model you use for your prediction or whatever purpose later on. So blindly considering all the attributes will make that model complex also, and that may bias the result of the prediction because of unnecessary information or insignificant information. So, and it is always obviously reducing the number of attributes will make the models more precise, less complex, and that's why it will become more efficient. So that is why the idea of dimension reduction of a data matrix or matrix rather came up into picture. But when we do this dimensionality reduction, so we have to keep it in mind that we should not lose the information that is there in the original data set. So we want to minimize this loss of information, and still so we should have a smaller, let's say we can think of it like this, we can think of a smaller matrix with least information lost from the original matrix. So there are several techniques to do this reduction. So one of them is principal component analysis. So there are singular value decomposition and linear discriminant analysis. So although we have all those things in our syllabus, but due to this shortage of time and lots of holidays and things like that, uh, in this semester we'll be only considering one such example of dimension reduction, which is principal component analysis. So maybe singular value decomposition, you know how to do it, but probably I'm not sure if you have understood why singular value decomposition works. So in this class, our focus will be on how really principal component analysis works, not simply just how do you compute, why you compute in this fashion. So that is the focus today. Why principal component analysis optimizes the dimensionality reduction. So you can simply drop off some of the attributes, but you don't do it because if you do it randomly, then it is going to lose lots of information which are meaningful. So when you do principal component analysis, we can show mathematically that the information loss will be minimum. So that is what we are going to see today. Okay. So what I said just now is all given over here, dimensionality reduction. So the data matrix could be huge. So we need ways to summarize the matrix. So we need ways to summarize the matrix to smaller one for efficient processing, eliminating insignificant information. Okay. So now the process of identifying a smaller data matrix, the process of identifying a smaller data matrix is uh, that just 1 second. Yes. So the process of identifying this smaller data matrix that captures maximum information about the data set is dimensionality reduction. So as I said, these are the typical methods or techniques of doing the dimensionality reduction: principal component analysis, singular value decomposition, and linear discriminant analysis. But we are only going to concentrate on this PCA. So principal component analysis is basically a statistical tool again that uses an orthogonal transformation to convert a set of observations of possibly correlated variables into a set of values of linearly uncorrelated variables called principal components. Okay, so what is the meaning of this? So basically in principal component analysis, it is some kind of projection, but the projection is defined in a very different way. So we want to convert, so we want to produce an orthogonal transformation of the original matrix, which may contain many correlated variables, so into a set of values, uh, uh, into a set of values which are projected on a linearly uncorrelated variables called principal components. So you will later on you will see that all these principal components are actually orthogonal to each other. So that's why they're uncorrelated. Okay, so the principal components are uncorrelated. Basically, the principal component defines a coordinate system on which you are going to project your data set such that the information lost is minimum. Okay. So we will see more to it. So basically, principal component analysis is converting the set of converting that matrix into a smaller dimensional space, and this smaller dimensional space is identified by a set of orthogonal vectors, which are these principal components. And these vectors, the task is to find out these vectors where if you project the data set, then your loss is minimum. Okay. Now, how the loss is defined, we will see to it. How you are computing loss, or what your I mean, what is the terminology of loss? What you are saying? What should the loss of information? Okay. So I'm emphasizing again what I have said. So PCA reduces the dimension of the data by linearly transforming the data set into a new coordinate system. That's what I said, which is identified by those principal components. So this is what is the thing which we will define our loss on. So where most of the variances of the data can be described with fewer dimensions than the original data. So what loss we will be calculating? The variances. So the variances must be the coordinate system should be defined in such a way that most of the variances of the data will be captured. Okay. So this transformation is defined such that the first principal component has the largest possible variance. Okay, and each succeeding component has in turn the largest possible variance under the constraint that it is orthogonal to the preceding components. So this is what I said. Principal components are orthogonal to each other. Okay, so the first principal component is a direction that has the largest possible variance among all, and each succeeding component has in turn the largest possible variance under the constraint that all are orthogonal. Okay. So to explain this line once again in much more detail, So the principal components of a collection of points are a sequence of unit vectors. So since we are defining a coordinate system using this principal component, so it is it's a sequence of unit vectors in terms of unit vectors, where the ith vector is the direction of a line that fits the data while being orthogonal to the previous I minus 1 vectors. Sorry, so this will be vectors. Okay. So there is that again this question of where ith vector is the direction of a line that best fits the data while being orthogonal to the first I minus 1 vectors. Okay, now what is the meaning of this best fit? We will see it soon. So this principal component vectors, as we have discussed earlier also, it forms an uncorrelated orthogonal basis set. So you remember that basis set because basis set is required to represent any data into that plane or into that dimension defined by the basis set, right? Basis vectors. You remember basis vectors are some vectors using which the linear combination of all those vectors will tell you all the points in that data set. So obviously principal component should be such that, so they must be orthogonal and they must be basis vectors such that a linear combination of them will give you the original variables. Okay. So now come to the question of what is that best fitting line. So I mean best fitting line means the principal component vector. So line means basically we are talking about that vector. Okay, line is represented by the vector. So best fitting line is the one that minimizes the average squared perpendicular distance from the points to the line. So actually I could not draw the diagram over here, but maybe I can show it over here like this. Just a minute. Suppose okay, maybe I'll try to draw over here itself. So suppose you have this line. Okay. So this is the coordinate system over here, and you have a point over here which is xi. Okay. So we are talking about a two-dimensional vectors for ease of seeing it, because two dimension we can always visualize, right? So if this is your xi, so I am trying to find a line, meaning a vector, a principal component. So this is a line. Okay. So let's say it is a unit vector. Okay. So unit vector which represents this line. Okay. So what it says is that this average best fitting line, it is the line that minimizes the average squared perpendicular distances from the points to the line. Okay. So that means what? So that means basically you are finding a projection of this xi onto this line. So projection means always you are dropping a line perpendicular to this line L. So I want to find such a Q. What is that Q? So this is going to be one of this principal component, one of the principal component. Okay, and I want to minimize these distances. So this is di. So this distance, this perpendicular distance is di. Okay, so this distance, the distance of xi to the line. So I want to minimize this distance di. Okay, and I want to do it for all points in the data set. Okay, so for every point we'll be having such perpendicular distances and I want to minimize that. So that is what is best fitting line. It is the line that minimizes the average squared. Also we'll be doing a square, as I was saying, whenever we are having a minimization function or something like that. So this absolute term is not differentiable. It's not a continuous function. So that's why we do a squaring of it. So that's why we have this average squared, and we'll be doing a average of sum of all of them and divide by the number of points. Okay, so that is the best fitting line. So the question is how to find out such a kind of line. Okay. So now let's look at little bit, since we studied projection. So what is the difference between this projection versus this PCA? So if you look closely, I'm just talking in terms of 3D and 2D so that you can relate. So projection problem says, like, what does the 3D object look like from a particular place? Okay, what does this 3D object look like from here? But what PCA looks for is, what is the best 2D angle to see the most shape of the 3D data? So there is a difference. So in the first question, projection, I am fixing the position of my eye, or fixing the position of the camera from where I am looking at a 3D object and trying to project it onto a 2D plane. But in PCA, what we are trying to do is that so a 3D thing, you can see it from different angles, right? So in which so from some angle, many of the data points may become some kind of collinear, right? So in PCA, what it tries to see is that it tries to find from which angle you see, you will be able to see the maximum of the data points, meaning the maximum variances of the data points. Okay, so are you getting it, what I'm trying to say? Hello? Hello,
Yes,
are
ma'am.
you there? Okay. Yes. So, so a simple example is like this. So a snake in 3D. So a snake is identified giving some 3D data points. So after projection onto a 2D, it might look like a small circle when seen from certain point, let's say from front. But if you apply PCA, so it will automatically find the angle that shows the full long, that snaky kind of body of the snake, showing its maximum length and width. So this maximum length and width, we are talking it in terms of maximum variance. Okay. So that means what? I mean, this I already said. Projection maps 3D points onto a 2D surface based on a fixed viewpoint, while PCA projects data onto a new 2D plane designed to maximize the variance or information preserved from the original 3D structure. Okay. So here you can just kind of get a differentiate between this. So when you, with respect to this projection and PCA, so for projection, the goal is actually to visualize 3D data from a specific viewpoint. So whenever you do those visualization of 3D data using plots and things like that, then it uses actually projection. So in PCA, we reduce dimensionality, preserving the maximum variance. So then the selection of plane. So it is defined by the viewer or the camera position. And in PCA, it is chosen mathematically to match the data's shape. So that's why it is optimal. So you don't lose any information. Nothing obscures your view. So then the information loss in projection is high because we are just looking at it from a single point, from a fixed point. And in PCA, the information loss is minimized because we are trying to maximizing the variance of the data that we are trying to map. So then the projection is independent of the data. It is fixed because of this camera position or your eye position. But PCA is completely dependent on the data distribution. Okay. So the data distribution becomes very important over here. So in case of projection, the projections, I mean, it is not necessarily that it has to be that perpendicular perspective, but in PCA, the basis vectors are always orthogonal. Okay, so it always projects the data set onto orthogonal components. So these are the typical use, typically projection used in computer graphics, computer vision, and PCA is used in data science, machine learning, and data visualization at times. Okay. So, yes. So now, okay, let us remember once how you have computed principal component. Let's first look at the steps of computing the PCA. Then we will go and see how this is meaningful. So this is simply the steps are written over here, how you really compute a principal component, how you do a principal component analysis, or how do you find the principal components. So what we do essentially is consider a d-dimensional data set, let's say A n cross D with n entries. So then what we call doing a mean centering. So we compute mean for every column and subtract the mean from each element in that column. So we get a new matrix which is mean centered. So which I am denoting like this: xi1, xi2, xid, all bars. Okay, so each of them is a column, okay, which is mean centered. Okay, now let this new matrix be some x n cross d with, okay, so which is which is nothing but actually the original matrix minus the mean thing. Okay, so sorry, so this is not sorry, this is not the matrix, sorry, this is simply the average is written over here, right? So I've written it as a bar, sorry. So this is basically the mean of the first column, mean of the second column, mean of the third column, and then we subtract this from the original matrix, and so this is what is the mean centered data matrix. X is the mean centered data matrix. So then what we do is we compute the covariance matrix. So what is covariance matrix? Covariance matrix is this V, we are terming it as V, which is going to be definitely a D cross D matrix, because all the attributes, covariance between all possible pairs of the attributes. Okay. Obviously, covariance matrix, you all know, it is a symmetric matrix. So this, what we capture over here is the covariance between the different attributes. So possibly you can relate now, I was talking about capturing the maximum variance. So this maximum variance thing is actually related to this covariance. Okay. So then what you do is, once you have this covariance matrix, then you compute eigenvalues and eigenvectors of V. So why do you compute eigenvalues and eigenvectors? So that we are going to see now. What is the reason why we compute these eigenvalues and eigenvectors? So eigenvectors are, you know that since it is, this V is a symmetric matrix, eigenvectors are linearly independent. Okay, so these properties we saw in the last class. Okay, so then what we do is we sort the eigenvalues in decreasing order. So now remember why we sort it in decreasing order. You remember that Ax equal to lambda x. Lambda is your eigenvalue, right? So this lambda represents what? In this x direction, what is the maximum scaling value? If lambda is high, this lambda will be maximum. And this A is what in this case? Variance. I want to maximize the variance, right? So that is why we consider this, sort the eigenvalues in decreasing order, and highest eigenvalue corresponds to the maximum variance, right? And corresponding to that highest eigenvalue, the eigenvector, we consider it to be as a first principal component. And similarly, we look at the next decreasing eigenvalue that correspond to the second principal component, and so on. So this way you can keep on taking until and unless you are satisfied. Okay. So next what we do is that ultimately what we want to do, we want to map the entire n cross d dimensional data space into something into a smaller matrix of size, let's say n cross k, right? So we create a matrix which is called a projection matrix. So we create a matrix which is called projection matrix, this W, whose size is D cross K, and obviously K must be less than D. Okay, so K is the smaller dimension and D is the original dimension. Okay, so by choosing K eigenvectors corresponding to the decreasing eigenvalues in that order, and then we use this matrix, we use this set of eigenvectors arranged in a projection matrix to transform X to a new subspace of dimension K. Okay, so X dash, so this is our new smaller dimension reduced matrix, X dash, which is nothing but this X n cross D dot W D cross A. So this X dash is your new smaller matrix that has the maximum variance, but projected in a smaller number of dimensions, right? So I hope you remembered the steps of this PCA computation. So now we will see, basically we will emphasize on what is the importance of this. Okay, so let's go back over here. Okay, so so the objective is that given a matrix, the data matrix, okay, I have used here X. Actually, you can think of it as this A, n cross M. So this M is actually D that we saw over there. Okay, so find the best, so it is same, okay, don't get confused. So given this data matrix, find the best K less than M dimensional subspace with respect to X. So when we are talking about this subspace, again, remember that definition means it is a subspace which will, where all these data points you will be able to generated by those principal components. Okay, so that is the meaning. So we want to obtain the best least square fit that capture the variances. Okay, so here I've just written variances, but actually it is the covariance. Okay, so now again look at that figure which I have drawn earlier. So this is your point, let's say xi, okay, and this is the vector principal component that I'm looking for, which is a unit vector. Okay, and this is your projection over here. So this is what I'm calling it to be a yi, and this is actually called the projection of x on q. Okay, and this is the distance di, the perpendicular distance of xi on the L. So this is di. So now our simple geometric thing, what it says is that this length of projection, so it means basically this yi. So you can see, look at this length. So this is the length of the projection, right? So length of the projection of xi, the whole square, plus this perpendicular distance of xi to the line L square. So this is nothing but this. So this xi is actually, it has those components, right? xi2 and so on. In this case, it has only just two components, but it is in higher dimension, it will be many, right? So this means this is actually this xi1 square plus xi2 square plus all this xim square, right? So now this yi square plus di square, meaning this square plus this square, is equal to this square. Okay. Now this particular value, you will see that it is a constant value, because all these coordinates data points, these are, it is already given, right? So what is our objective? I want to minimize this distance. I want to find a line L such that the distance of all points to the line is minimized, right? I want to find such a line. So that means what? I want to minimize actually this di square. So minimize di square means, if I just write it in the other way, that means di square is nothing but this, all these xi1 square plus xi2 square and so on, minus yi square, right? So minimize di square, minimize this di square essentially means, so you see there is a subtraction over here. So some constant, so this is a constant minus some yi square. So yi square is this, what is the projection? So if I have to minimize di, so that means I have to maximize this thing, then only the difference between these two will be less, right? So that means minimizing di square means actually maximize this projection, maximize the projection square. So, and this is what is a variance, right? You see, that is what is the variance. Variance among that is what is actually the variance. So we want to maximize this yi square, right? So now, with this, let's look at now how the formula for this maximization of yi comes out. I mean, how do you maximize this yi square? Okay. So now let's consider this xn be mean centered, meaning that I'm talking about now this particular xn cross d. Instead of saying d, I'm saying here it is n. That's all. So it is mean centered. So from a, meaning that you have converted that matrix to a mean centered. So this is done so that your computation becomes little easier. Okay, so because it has different, all the attributes may be having some different scaling. So kind of standardizing and centering it to zero so that, centering it to the mean so that your expression becomes much more easier. For example, how this mean centering helps, you see. So variance, how it is defined? Variance is defined like this: 1 by n summation I is equal to 1 to n xi minus x bar the whole square. So if you have mean centered, then what is going to happen is that this particular thing, now we can consider it to be a, since this part we have already done, right? This xi minus x bar thing we have already done, and the value is present in that form. So that is nothing but your this yi square. Okay. So so over here, so this variance, so this is what is your variance: 1 by n I is equal to 1 to n, simply yi square. So this is the reason, that's why we have done this mean centering. Okay. So now, so what, don't forget the objective. I want to find this line. Finding this line means actually finding out what is this vector q, what is this q vector along which the variance is maximum. Okay. So so the step that we did is, variance is nothing but this projection that we came up. Okay. So now let this q denote a unit vector along line L. So now we need to see what is the projection of xi on this line q. So from this linear algebra technique that we know that the projection of yi of xi on this L is nothing but, so this yi. So this yi, we can write it as xi transpose q. Q is a vector, xi is also a vector, right? So xi transpose q, where xi is this. Okay, so xi transpose q. Q is a unit vector, don't forget that. So now, now if I substitute this yi into our equation, which we want to maximize, so then what it mean squared projection v is 1 by n summation I is equal to 1 to n, sorry, here it will be yi square. So this is equal to, just simply I have put this yi to over here, xi transpose q the whole square. Okay, the value of yi I have just put over here, xi transpose q the whole square. Okay, so after this, actually, I haven't finished preparing the slides. So what I will do is I will write it down over here now. The next thing. Okay, let me just open a new discard. Okay. So the handwriting will be little bad, but okay, can't help it now. So what we saw was this. So what we wanted to do is that maximize maximize v equal to 1 by n summation I is equal to 1 to n xi transpose q the whole square. Okay. Now this variance, obviously it must be greater than equal to 0 because I am doing a square. Okay. So now you see that, so we know that this xi transpose q is same as q transpose xi. So actually I need to write it in a different fashion for our computation purposes. So we can write v equal to 1 by n summation I is equal to 1 to n q transpose xi into xi transpose q. Okay, so I'm just writing this thing xi transpose q the whole square as two things because these two are same. Okay. So now this can be written as so this we can write it as this q transpose I'm writing outside, then I'm writing one. So actually what I'm trying to do is that scalar components, scalar values, I'm trying to put it in one place. Okay. So this q transpose I'm taking over here and this q I'm taking over here, this q. And then rest of the things I'm writing it like this, 1 by n summation I is equal to 1 to n. Okay, I'm not writing I equal to 1 to n each time. It is understood now. So xi into xi transpose. So you know that xi into xi transpose, it is just going to be xi are those data values, right? So this is going to be a square value, scalar value. 1 by n into something is going to be some scalar value. Okay, so let's say that scalar value I am writing a constant value, right? It depends on the data. So this c value is going to be, let's say I'm considering this to be c equal to this summation xi transpose, sorry, the summation xi transpose. And notice that now, what is this? This is actually the covariance matrix that we are talking about, that we talked about in the steps to compute the eigenvalues. Okay, so the covariance matrix, you know, it's the relationship between the different attributes. So this is what is going to reflect that covariance. So here I've taken it with single variable, but you can take it with another variable, right? So this is what is going to give you your covariance matrix, a mean-centered covariance matrix. Okay, mean-centered covariance matrix. So now let's look at this. And since we know that covariance matrix is symmetric, so covariance matrix is symmetric. right? So meaning C transpose equal to C. So this will help us to do some maths. So now what is it? We want to find that, sorry, we want to find that vector, unit vector Q, along which that variance, this variance is maximized. Okay. Q, which is the unit vector along which V is maximized. Okay. So now what it becomes, this maximization of V. See, we started with this V equal to 1 by N and so on. So we want to maximize, sorry, maximize V. So maximize V. So that comes out to be then what? So this Q transpose into this entire thing, I'm calling it to be C and then Q. Okay. Subject to the constraint. So subject to constraint that, so norm. This norm means what? Basically, it is that square root of its components actually. X1 square, X2 square and so on. So this norm means the Euclidean norm, okay, the magnitude. Okay. So this is the norm or magnitude. Magnitude of this is equal to 1 because we are talking about a unit vector. Okay. Or you can think of it like Q transpose Q equal to 1. Okay, because it is a unit vector, so this is going to be 1. So now this type of optimization problem is what is called a constraint optimization problem. So you remember that in linear regression, we have solved optimization problem. We wanted to minimize the least square, right? We wanted to minimize the errors, right? So what we did that differentiation equating to 0 and then getting the values of those parameters. But there was no constraint. Like there was simply a equation like this, and then we did the minimization of it by doing the differentiation and equating to 0. But in this case, there is an objective function this, but there is also a subject to constraint that Q transpose Q equal to 1. So in order to solve such problem, there is a particular method. So solving this constraint optimization problem. So solving this constraint optimization problem is a bit, there are some more steps along with this differentiation and things like that. In fact, before doing the differentiation, somehow we have to add this constraint to this objective function of maximization of V. So are you there with me? I haven't asked for a long time. Hello?
Yes, ma'am. Yes, ma'am.
Okay. So this constraint, somehow I have to do something into the objective. I have to bring that constraint into the objective function. So the method to, so basically what we are trying to do is that bring the constraint into the objective function, this maximization of V. Okay, so the step to do it is what is called a Lagrangian multiplier. So we use for this what is called a Lagrangian multiplier. Which is basically a scalar value lambda. Okay. So this scalar value, with this scalar value, so now the objective function becomes like this with the constraint. I have to take a new page. So the objective function now becomes like this. Maximize V dashed, which is Q transpose C times Q minus lambda times that thing Q transpose Q. So Q transpose Q must be 1. Okay. So in order to bring that into this objective function, what we do is Q transpose Q minus 1. So it must be actually 0. Q transpose Q minus 1 must be near about 0. Right? So that's why we write it in this fashion. Q transpose Q minus 1 into some scalar lambda. Okay. So once this is using that Lagrange. So this is the way you use Lagrange multiplier in order to add the constant into the maximization function. Okay. So so there is a lot more theoretical things in order to understand what is Lagrangian multiplier, and it is the same. So we are not going in that details. So next what we will apply is our finding out the derivative and equating to 0. So what we will next do is find this del B dash delta Q. So that becomes what? Then you see. So this Q transpose, so C is a constant, right? But this Q transpose and Q is essentially, it is square, Q square, right? So that's why when you do the differentiation, Q squares 2 comes over here, and we can write Q transpose C minus this lambda will be coming into picture, and again this Q square. So minus 2 lambda Q transpose. Okay, and this minus 1 is going to be 0, lambda and 1, so that is 0. So now we have to equate it to 0 in order to get the Q. So what we get is that 2 or 2Q transpose C equal to 2 lambda Q transpose. Okay. So what you get now is that this 2 you can just eliminate. Then what you see, just see, this is something nice that you can, if you can observe. What ultimately we are getting is Q transpose into, okay, let me write it in this fashion. C is a matrix, don't forget. C, sorry, I should not write in this fashion. The dimension will get wrong. So Q transpose C equal to lambda Q transpose. Do you see anything over here? Does this form looks familiar? C is a matrix, Q transpose is a vector, and here lambda is a scalar, Q transpose is a vector. Do you see anything? This is the most important part of this theory. You still are not able to see anything. Okay, let's apply a transpose to it. Apply transpose on both sides. So what do you get? C times Q lambda times Q. Do you see anything now?
And like eigenvalue computation.
Yes, it's the expression for eigenvalue, eigenvectors, right? So you are operating a unit vector Q on this matrix C, and as a result, if you remember the interpretation of eigenvalues and eigenvector, you are scaling it in the direction of the Q by lambda, right? And this, so this C is the covariance matrix and lambda is the scaling factor along this Q vector where the change, the maximum variance has been obtained, right? So that is why actually you compute the covariance matrix, and after computing the covariance matrix, you find the eigenvalues. Then among the eigenvalues which has the highest eigenvalue, for that you find the eigenvector, and that is your principal component, first principal component. Second eigenvalue you take, that is your second principal component. And since this C is a symmetric matrix, all these eigenvectors are going to be linearly independent and orthogonal to each other. That's why they will form a basis vector, and that's why it will span the entire space of, entire row space of the original matrix X that you have considered. Okay. So the eigenvector Q of C gives the line that maximizes the variance okay. So what we saw is that this maximizes the variance. One more small thing that you need to really see. What is that? That is, now look back at the. We will again go back to that figure. We'll go back to this figure that I have drawn. So this is that xi, this is that q, this is that di projection, yi is the projection, and what we wrote was that yi. So if you look at like this vector equation, okay. So what we can write is that di plus this yiq, okay, because q is a unit vector and yi is the amount of projection, right? So we can write this particular vector from with the magnitude, this yi represents the magnitude of this, so we can write it like this, that di plus yiq equal to this one, which is xi. Okay. So so we are going back to that, right? So we started with this distance, minimizing this distance, right? That is where we started with. And from there, we said minimization of this distance means actually maximization of this variance. And that way we came up with the formula for finding out the principal component. So let's look at once again from that angle also. So now it becomes xi minus yi into q, right? So now this distance, we can write it in the form of a norm, okay? This can also be written, since di is this, we can write it like this, xi minus yiq. So whenever I'm writing it as a norm, that means it is that square form, Euclidean distance form, okay? So now we know that yi is equal to xi transpose q, okay? So we can write it as now this norm di is, I'm simply substituting it, nothing else, yi xi minus, yes, so yi is what? Xi, sorry. So instead of yi, I am writing it as xi transpose q into q, okay? So when I write it as di square, so that means we can write it in this fashion now, xi minus xi transpose q into q, this entire thing transpose into squaring it, right? Squaring it means we can always write it as that particular element transpose and that element. So again, xi minus xi transpose q, q. Now we will simply do some algebra, matrix algebra. So just multiply xi. So I'm applying this transpose on this particular and then multiplying with this. So xi transpose xi minus xi transpose q into q minus xi q transpose xi plus xi q transpose xi transpose q into q. So if I just mark them 1, 2, this is 3, 4. So what I have done basically over here is that this is 1 multiplied by 2, this is 1 multiplied by 4, second one is, so this component is 2 and 3, and this is 2 and 4, okay? Nothing else, simply this did the algebra. Now you notice that since now we'll do some more algebraic manipulation. So xi transpose q is again same as q transpose xi, okay? And this value is a scalar and this is scalar. You understand, because this is a row matrix and this is a column matrix. So multiplying these two matrices is going to be a scalar value, okay? So now what we can write, so remember that we are writing di square equal to, right? So I'm again writing that di square is equal to, so the first term will be coming over here, xi transpose xi, okay? Then minus, so these two, because of this, xi transpose q is q transpose xi. So that means these two terms, we can write it as 2 times xi transpose q, the whole square, right? Plus, the other thing is what? So here, this term is again xi to q transpose, and here again q xi transpose. And this q and q transpose, these are unit vectors. So that means when you multiply them, it becomes 1. So that means this part becomes xi transpose q the whole square. So that means this becomes xi transpose xi, yes, xi transpose xi minus, because this is a minus sign over here. So xi transpose q the whole square. Okay. So this is for a single variable we are doing xi. Now we are going to do the average distance square, right? Average of all I distances, average of all n distances, in fact. Okay. So that d, if I write it, so it becomes 1 by n summation I is equal to 1 to n di square. So that is 1 by n into summation I is equal to 1 to n xi transpose xi minus, what is it? Xi transpose q the whole square. So that means it is the variance. Okay. So what I want to simply show you is that where we started, we are getting again back to that. Okay. So what it implies is maximization of variance, maximization of variance. So we have maximized this, right? This thing we have maximized using all this. So maximization of variance, meaning minimization of mean squared distance t to x's. Okay, so from both sides we saw how principal component analysis really work in this context. So sorry, cancel. Okay, let me show it in that. Yes. So is it okay? Did you understand? So let me go back to our original presentation. Okay, so now again, let's come back to this principal component analysis steps now. So consider this d-dimensional data set. So essentially we have tried to maximize the variance, although our main intention was minimizing the distance of all points to a unit vector line. Okay, so from there we went to what is the maximization of the variance, which essentially means maximizing the projection of xi onto the line where the variance is maximized. Okay, so again, let's come back to the steps of computing the PCA. So we consider d-dimensional set, compute the mean of each column, then compute the covariance matrix. So this covariance matrix VDD is same as the one over here. So there we have just done with only single variable x, but when you take the covariance matrix, it is between each possible pair of variables or attributes where whose variance you are actually looking at. Okay, so this matrix is a symmetric matrix. Then what you do is compute eigenvalues and eigenvectors of V. So this is what we saw. Why we really compute this V? Because when we try to, this variance is nothing but the projection of this data points onto a line, right? And that projection, when you try to maximize it, it comes down to a formulation of the eigenvectors. Essentially, you try to see along which vector your variance is maximum. Variance is maximum is identified by this lambda value, the scalar value lambda, along which vector that lambda is the maximum. And the highest lambda is going to give you the vector where your variance is maximum, and slowly the next level you can find other principal components, and depending on your requirement, how many principal components or how much you are satisfied with, or how much your computation ability is on the machine. Depending on that, you can decide on how many principal components you are going to take. So obviously, if you take all the principal components, then what is going to happen is it is simply the entire matrix again back. So you don't really reduce the dimension. I mean, what I mean is, if you consider K to be same as this D, but if you take K which is less than D, definitely you reduce the dimension. But how many Ks you will go, that depends upon you, depending on your problem requirement. Okay. So, and this projection matrix will help you to compute the, the new or the transformed points into the new space with dimension K, using this formulation X. So the original matrix dot product, multiply with the this projection matrix, which is nothing but the K eigenvectors in decreasing eigenvalues, ordered in decreasing eigenvalues. Okay, so to sum up, so what are the kind of merits, demerits you can think of about this principal component matrix? So one point is that, can we get back to the original matrix A from this transformed matrix? So X dashed is the transform matrix. The data after mapping it to the new coordinate systems of the principal components. Okay. So now, if all D eigenvectors are available, then obviously you can apply a reverse transformation, and you will get back this A cap equal to X dash WT plus A bar. What is that A bar? You remember, we have to ultimately do that mean centering again back to get the original matrix. So we have done a mean centering before applying the transformation. So that's why, in order to get the original matrix, we will be getting, you have to add this X bars, the means, after doing the reverse projection using this X dashed WT thing. Okay, but what might happen is, because of this floating point error kind of thing, you may not get exactly the original matrix because of this floating point problem, because lots of matrix multiplications is going on, and the values may not remain always integer. But theoretically, yes, of course, if you have really a high precision kind of machine computations, then you can get the original. If you use all the eigenvectors, if all D eigenvectors, not the K eigenvectors, D eigenvectors, means originally the dimensions of the data. Okay, so the merits, what we can say is that PCA works best for dimensionality reduction when attributes are highly correlated. Um, um, PCA helps obviously in data compression. Then it eliminates components with low variance. So low variance actually means that the values are almost having no impact on the entire thing, right? So that is what is the meaning of low variance. So those attributes can be obviously eliminated because they will be on the lower side of this principal components, later part of the principal components. So it also helps identifying outlier by showing which point significantly deviates in the reduced space. Okay. And so what are the kind of demerits? So one thing is that in order for PCA to work properly, it will need proper scaling. So like mean centered data or some kind of standardization of all attributes. I mean, if your one attribute is in the scale of 0 to 10, another attribute is in the scale of, let's say, 1 lakh and 2 lakh, obviously that will require some kind of standardization. Otherwise, the floating point errors will be, not errors, floating point computations will be, will make things much more, what should I say? It will not reflect the true nature of the variance in that case. So this proper scaling is required if your attributes are varying too much in their range of values. So that is one pre-processing that you need to do before you apply your PCA. So then if number of principal components chosen are small, then there obviously may be information loss that you need to check and see depending on the requirement. And PCA works well if the relationship between attributes are linear. So if so non-linear relationships, obviously you cannot capture using this PCA. I mean, if you want to do the dimensionality reduction where features are non-linear, actually those features are important. You cannot reduce them. Okay. And then it may be slow for large data set, obviously. And if too many components are chosen or data set is too big, too small, then PCA may not be very effective, obviously. So that is all I have today. So you have anything to ask? Hello, are you there with me? আছো কি তোমরা নাকি সবাই চলে গেছে?
Yes, ma'am.
ঠিক আছে, বোঝা গেল কিছু?
Yes, ma'am.
ওকে ওকে, তাহলে আমাকে একটু অ্যাটেন্ডেন্সটা দিয়ে দিও।
ওকে ম্যাম।
ঠিক আছে, তাহলে আবার পরের ক্লাসে হবে। আর আমি ওই কিছু আপডেট করেছি আর কিছু আরেকটা অ্যাসাইনমেন্ট দিয়েছি, সেটা একটু দেখে নিও অ্যাসাইনমেন্টটা কি আছে।
ওকে ম্যাম।
Okay, ma'am.
ঠিক আছে, অ্যাটেন্ডেন্সটা দিয়ে দিও, আমি বেরিয়ে যাচ্ছি তাহলে। হ্যাঁ,
ঠিক আছে ম্যাম।
Thank you.
ঠিক আছে ম্যাম।
এবার স্ক্রিনশট নিচ্ছি, সব বেরিয়ে গেছে নাকি?
বের হচ্ছে সব আস্তে আস্তে।
বহুত তারা জীবনে এদের। আমি স্ক্রিনশট নিয়ে নিই। বেরিয়ে যা।